Lecture 1C on the area of a triangle and quadrilateral given vertices. The area of a triangle with vertices A x1 y1, B x2 y2, and C x3 y3 is given by area of triangle ABC is equal to half times absolute value of x1 times y2 minus y3 plus x2 times y3 minus y1 plus x3 times y1 minus y2. Or in determinant form, area of triangle ABC is equal to half times the absolute value of the determinant of the matrix with x1, x2, x3 in row 1, y1, y2, y3 in row 2, and 1, 1, 1 in row 3. The proof. Draw the triangle with vertices A, B, and C. Let this be the y-axis and this be the x-axis. Then project the point B on the x-axis and let us name that point D. Project the point A on the x-axis and name the point E. And also project the point C on the x-axis and name the point F. Clearly, the distance from D to E is x1 minus x2. The distance from E to F is x3 minus x1. And the distance from D to F is x3 minus x2. Clearly, to find the area of triangle ABC, we have to find the area of these three trapezium. Trapezium A, B, D, E, trapezium A, C, F, E, and then trapezium B, D, F, C. Observe that these two trapezium, this trapezium and this one, covers the triangle. And if we cut off this other trapezium, we'll have the area of triangle ABC. So let us find the area of the three trapeziums. Area of trapezium ABDE, that's this trapezium ABDE, is equal to half BD plus AE times DE. Recall, area of a trapezium is half the sum of the parallel sides times the height. And this is equal to half times BD from B to D is y2 plus AE from A to E is y1, then times the height DE, which is equal to x1 minus x2. Area of trapezium AEFC, that's this trapezium AEFC, is equal to half of CF, that's CF plus AE times the height EF. And this is equal to half into CF is y3 plus AE is y1 then times the height EF, which is x3 minus x1. And finally, area of trapezium BDFC, that's this trapezium BDFC, is equal to half of BD plus CF times the height DF. This is equal to half into BD is y2 plus CF is y3 times the height DF, which is x3 minus x2. Therefore, area of triangle ABC is equal to area of trapezium ABDE plus area of trapezium AEFC minus area of trapezium BDFC, which is equal to half into y2 plus y1 times x1 minus x2 plus half into y3 plus y1 times x3 minus x1 minus half into y2 plus y3 times x3 minus x2. Multiplying the terms in bracket out and collecting terms in x1, x2 and x3 together, we have half into x1 in bracket y2 plus y1 minus y3 minus y1 plus x2 into y2 plus y3 minus y2 minus y1 plus x3 into y3 plus y1 minus y2 minus y3. Observe that here y1 will cancel y1, here y2 will cancel y2, and here y3 will cancel y3. This will then give us half into the absolute value of x1 into y2 minus y3 plus x2 into y3 minus y1 plus x3 into y1 minus y2. Example 1. Find the area of triangle ABC whose vertices are A 1 3, B 5 1 and C 3 7. Solution. Let the first point x1 y1 equals to the point 1 3, x2 y2 equals to the second point 5 1, and x3 y3 equal to the third point 3 7. Then recall the area of triangle ABC is equal to half times the absolute value of the determinant of the matrix consisting of x1, x2, x3 in the first row, that is 1 5 3, y1, y2, y3 in the second row, that is 3 1 7, and 1 1 1 in the third row. Evaluating this determinant using any known method, here we are using the cofactors method. Expanding using row 1, this will give us half times absolute value of 1 into 1 times 1 minus 7 times 1, that is 1 minus 7, plus 5 into 7 times 1 minus 3 times 1, which is 7 minus 3, plus 3 into 3 times 1 minus 1 times 1, that is 3 minus 1. This will give us half times the absolute value of 1 minus 7 is minus 6 times 1. That will give us minus 6. 7 minus 3 is 4 times 5. That will give us plus 20. Then 3 minus 1 is 2. And 2 times 3 is plus 6. Here, minus 6 plus 6 will cancel out. So absolute value of 20 is 20. Then half of 20 will give us 10 square unit. So that is the required area of triangle ABC. Example 2. Find the area of the quadrilateral ABCD whose vertices are A 0,3, B 3,1, C 10,2, and D 6,10. Solution. Let us sketch the quadrilateral ABCD as follows. This is quadrilateral ABCD. To find the area of this quadrilateral, we have to partition it into two triangles. We partition it at the point BD. So joining B and D, we now have two triangles, triangle ABD and triangle BCD. In triangle ABD, let x1, y1 be the vertex A with coordinate 0, 3. x2, y2 be the vertex B with coordinate 3, 1. And x3, y3 be the vertex D with coordinate 6, 10. Putting this into the formula for the area of a triangle given vertices, area of triangle ABD is equal to half times the absolute value of the determinant of x1, x2, x3, that is 0, 3, 6 in row 1, y1, y2, y3, that is 3, 1, 10 in row 2, and then 1, 1, 1 in row 3. Evaluating this determinant and multiplying by half will give us 16.5 square unit. Also in triangle BCD, let x1, y1 be the point B with coordinate 3, 1. x2, y2 be the point C with coordinate 10, 2. And x3, y3 be the point D with coordinate 6, 10. Therefore, area of triangle BCD is equal to half times the absolute value of the determinant of the matrix with x1, x2, x3 in row 1, that is 3, 10, 6, y1, y2, y3 in row 2, that is 1, 2, 10, and 1, 1, 1 in row 3. Evaluating this determinant and multiplying by half will give us 30 square unit. So therefore, the area of quadrilateral ABCD is equal to the area of triangle ABD plus area of triangle BCD, which is equal to 16.5 plus 30 square unit. And this is equal to 46.5 square unit.